Earth, our home, is a tiny blue dot amidst the vast cosmos. All human life, history, and culture are confined to this planet, a fragile sphere in the immense expanse of space. Let's explore this journey with scientific detail to appreciate the enormity of our universe. The Moon, about 384,400 km away, is our first stop. This distance, while manageable on a cosmic scale, is daunting in practical terms. Light takes about 1.28 seconds to travel from the Moon to Earth. From the Moon's surface, Earth looks like a delicate blue orb, emphasizing the fragility of our existence. Next is the Sun, at an average distance of 1 astronomical unit O, or roughly 150 million km. Light from the Sun takes about 8 minutes and 20 seconds to reach Earth. The Sun's immense energy is produced by nuclear fusion in its core, where hydrogen atoms fuse to form helium, releasing vast amounts of energy. This fusion process has sustained the Sun for about 4.6 billion years and will continue for several billion more. Mars, our neighboring planet, ranges from 54.6 million km to 401 million km away, depending on the alignment of orbits. The challenges of reaching Mars are not just about distance, but also about timing and orbital dynamics. The thin Martian atmosphere, composed mostly of carbon dioxide, presents difficulties for landing spacecraft, while its surface hints at a wetter past with potential for life. Neptune, the outermost planet, is about 4.5 billion km from Earth. Sunlight takes over 4 hours to reach this icy giant. Beyond Neptune lies the Kuiper Belt and the hypothesized Oort cloud, a vast region of icy bodies that marks the edge of the Sun's gravitational influence. The Voyager 1 spacecraft, humanity's farthest traveler, has crossed into interstellar space, more than 22 billion km from Earth. The closest star system, Alpha Centauri, is about 4.4 light-years away, or 41.3 trillion km. At current spacecraft speeds, reaching Alpha Centauri would take tens of thousands of years. Light years, the distance light travels in a year 9.46 trillion km, are the preferred unit for such immense distances. Our galaxy, the Milky Way, spans 100,000 light-years and contains over 100 billion stars, many with planetary systems. The radio bubble, a sphere about 100 light-years in radius, marks the extent of humanity's electromagnetic signals. Beyond this, our presence in the universe remains undetected. The Milky Way is part of the Local Group, a cluster of more than 50 galaxies within 10 million light-years. This group is a small part of the Virgo supercluster, which spans 110 million light-years. The Virgo supercluster itself is a segment of the Laniakea supercluster, a structure over 500 million light-years across, containing hundreds of thousands of galaxies. The observable universe spans 93 billion light-years, a result of cosmic expansion since the Big Bang 13.8 billion years ago. While the universe is finite in age, space itself has stretched, allowing distant galaxies to move beyond the speed of light relative to us. This expansion creates a boundary beyond which we cannot see or interact. Challenges of traveling to distant galaxies. Galaxies are separated by vast expanses of space, measured in millions to billions of light-years. For example, the closest galaxy to the Milky Way, Andromeda, is about 2.5 million light-years away. The edge of the observable universe is 46.5 billion light-years away. Traveling such distances at the speeds possible with current technology is impractical. The Voyager 1 spacecraft, traveling at about 17 kilometers per second, would take 70,000 years to reach even the closest star, Alpha Centauri. At this speed, reaching Andromeda would take billions of years. Energy requirements. Propelling a spacecraft to even a fraction of the speed of light requires vast amounts of energy. Achieving 10% of the speed of light, 0.1 c, for a small spacecraft would require energy equivalent to billions of tons of TNT. For a large, crewed mission, the energy demands are exponentially higher. Time dilation. If we achieve speeds near the speed of light, using Einstein's theory of relativity, time dilation would occur. For the crew, time would pass more slowly compared to observers on Earth. For example, a journey to a distant galaxy might take a few years from the crew's perspective, but could span millions of years on Earth. Cosmic hazards radiation. Traveling through intergalactic space exposes travelers to cosmic rays and high-energy particles collisions. Even microscopic particles at high speeds could cause catastrophic damage to a spacecraft resources. Sustaining life over vast time spans would require closed-loop ecosystems or generational ships. Future theories and technologies for galactic travel. Antimatter propulsion. Antimatter reactions are the most energy-dense processes we know, converting mass into energy efficiently. However, producing and storing antimatter is technologically challenging. Current facilities can produce only minuscule amounts of antimatter. Theoretical concepts like the Alcubierre warp drive suggest bending spacetime to achieve faster-than-light travel. A warp drive contracts spacetime in front of the spacecraft and expands it behind, allowing faster-than-light travel without violating Einstein's relativity. Challenges include creating and controlling the negative energy or exotic matter required to manipulate spacetime. For slower journeys, generation ships could house populations that live and die over generations while the spacecraft continues its voyage. However, maintaining a stable society and resources over millennia is a daunting challenge. Wormholes are hypothetical shortcuts through spacetime, could connect distant regions of the universe. Predicted by Einstein's general theory of relativity, they require immense energy and exotic matter to stabilize. Even if they exist, traversing them without catastrophic collapse is uncertain. Quantum phenomena like tunneling and entanglement hint at exotic possibilities for bypassing spatial distances. However, quantum teleportation currently applies only to information, not matter. Scaling these phenomena to macroscopic levels remains purely speculative. The concept of traveling out of the universe is speculative and rooted in theories like the multiverse or higher dimensional space. Here's what we know. The observable universe versus entire universe. The observable universe is a finite region we can see, limited by the speed of light, and the age of the universe, 13.8 billion years. Beyond this, the universe could be infinite. Expansion ensures some regions will forever remain out of reach. Some theories, like string theory or cosmic inflation, suggest the existence of multiple universes. These universes might have different physical laws or constants. There is no known mechanism for traveling between universes. Higher dimensions theories like M-theory propose additional spatial dimensions beyond the familiar three. If accessible, higher dimensions could provide shortcuts to distant regions of space or other universes. Currently, there is no experimental evidence for these dimensions. According to the laws of physics, speed of light, no object with mass can travel faster than light in normal space. Energy limits. The energy required to reach significant fractions of the speed of light grows exponentially. Cosmic expansion. Space itself is expanding, making some regions of the universe unreachable as they recede faster than the speed of light. According to the laws of physics, no object with mass can travel faster than light in normal space. The energy required to reach significant fractions of the speed of light grows exponentially. Space itself is expanding, making some regions of the universe unreachable as they recede faster than the speed of light. What lies beyond the observable universe remains a profound mystery. Some regions of space expand so rapidly that their light will never reach us, leaving them forever out of reach. This humbling reality reminds us of our tiny place in the cosmos and the vastness that still remains to be understood. Conclusion. While traveling to distant galaxies or beyond the universe is beyond our current technological and theoretical capabilities, ongoing advancements in physics, engineering, and cosmology may one day open new possibilities. For now, Such journeys remain a tantalizing vision of the future, inspiring humanity's quest to understand and explore the cosmos.